In this video, we're going to start by looking at how we evaluate the quality of a set of measurements. And the word set here is actually important. Equivalent measurements are usually made multiple times, or what we call in replicate, so that we can average over the multiple measurements and ideally cancel out errors that happen in any particular measurement process. This average of repeated measurements turns out to be our best guess of the true value. Now, the standard deviation of a set of equivalent measurements or replicate measurements captures the spread or uncertainty of the set. We're going to return to this point here in a second, but this is also related to measurement quality. So there are sort of two dimensions to measurement quality here. There's how close is that mean, the average of the repeated measurements, to a true value, reference value, standard value that we know, and how much spread is there within the set of equivalent measurements themselves. This is a purely internal measure of measurement quality. If errors are low, we would expect all the measurements to appear roughly at the same spot, right, on our hypothetical number line where we're laying down a range to establish the measurement. These two dimensions of measurement quality are known as accuracy and precision. Accuracy is the closeness of that average to a previously measured or reference value. Precision refers to the closeness of the measurements to each other without any reference to an outside value. This is often represented using sort of a target demonstration like you see here at the bottom of this slide. We've got three sets of measurements. The measurements are the black dots on each target. And let's imagine that the center of the target is our true value, reference value, standard value, whatever you want to call it. We can evaluate the accuracy and precision of each set of black dots. Let's start with the idea of accuracy. And to show this, I'm going to draw a purple dot at the center of each target and a second purple dot at the approximate spatial average of the black data points. So here, for example, this is roughly in the middle of these three data points. Same idea here and same idea here. And the length of the line segment that connects those two purple dots is a measure of the deviation of the average of the data set from our true value or reference value at the center of the target. So from the lengths of these line segments, we can get a sense of accuracy, right? The shorter that line is, the more accurate the data is. So the most accurate data set is on the left. The measurements are closest to the center of the target. And the least accurate data set is on the right. That middle data set is sort of in the middle. Now, what about precision? Well, precision is entirely about the spread within the data itself. How close are the data points to each other? To get a qualitative sense of this, we can kind of draw a halo or highlighting around the measurements and look at how big that highlighting is. And so here again, if we look at the leftmost data set, the points are relatively close together. They're clustered around the mean. They're all very close to the mean. This is how we're going to evaluate precision quantitatively here in a second. And then on the right, we have three data points that are much more spread out. They're all relatively far from the mean and far from each other. And so the most precise data set is the one with those points closest to one another on the left. The least precise data set has the points spread out on the right. And notice these blobs of highlighting that I've drawn around the data points have nothing to do with the reference or true value at the center of the target. This order of precision would still hold true even if the mean of these three dots was sitting right over the center line. The data would still lack precision even if the mean was accurate. And so in this sense, accuracy and precision are independent concepts, independent ideas. Data can be precise but not accurate but not precise, both accurate and precise, etc., etc. We express accuracy quantitatively, essentially as the line of this, as the length of this line segment. What is the distance of the mean value from our reference or true value? And on the slide here, we're going to call the mean x bar. This bar over x indicates that I'm averaging over a set of x values, and x ref is our true or reference value. To find the deviation of the mean from the reference value, this is entirely a one-dimensional thing, right? We're thinking on our number line corresponding to the phenomenon of interest. That deviation goes in the numerator of this calculation, but the size of that deviation depends on the units we're using, right? That is going to be a measurement in and of itself with units. And to get rid of the units, which requires us to think about how big is a gram, how big is a meter, things like this that we don't want to think about, we divide by the reference value. This expresses the deviation as a percentage of the reference value, and this measure is known as percent error. It's a very standard, very common measure of the accuracy of a set of data. This may be signed or just positive. It's usually expressed just as a positive quantity, but if we're interested in whether the mean is larger or smaller than the reference value, you might see percent error expressed as a positive or negative quantity. We noted earlier that precision is all about the deviation of each data point from the mean and the size of that. And this is a step toward how we quantify precision using the idea of standard deviation, or sigma. This is a concept from statistics that is based on the deviation of each data point from the mean. You'll see that in the formula for standard deviation here. We're taking each data point and subtracting it from the mean value. But we square that and we add all those squares up over all the data points and then divide by the number of measurements we made, which is this capital N. What's under the square root gives us the average squared deviation of each point from the mean, and the square root just removes that squaring, essentially. What squaring does is really emphasizes relatively large deviations. Instead of the deviation being 3, right, the square of the deviation is 3 squared, or 9, and as the deviation gets bigger, the square gets bigger faster. So the standard deviation is a rather unforgiving measure of precision in that sense. But notice that since we're just taking a difference between two measurements, we're squaring it and then taking the square root of it, the units of standard deviation are the same as the measurements themselves. So if we did a bunch of measurements in units of grams, the standard deviation would have units of grams. And unsurprisingly, given that the deviation of each data point from the mean shows up in here, the larger the standard deviation, the greater the spread in the data. When you see a measurement or the mean of a set of measurements reported with plus or minus a value, this is usually the standard deviation, plus or minus sigma, as we saw previously, or you might see this convention where digits inside parentheses indicate the magnitude of the standard deviation with respect to those rightmost digits in the mean. And speaking of precision, in the remainder of this video, we're going to talk about significant digits. Significant digits are really used as a kind of shorthand in science to make sure that we're not expressing our results with false precision. The more digits a number has in it, the more precise it is, right? If we go back to the target example, if you imagine expressing each data point, say, as an x-coordinate and a y-coordinate, the more numbers we have in those x and y values, the more we're sort of zooming in on the target and specifying a very detailed position for the data point. And if all of our points have a lot of digits and a lot of those digits are the same, we're looking at highly precise data. So data and results with a lot of digits evoke this idea of high precision. But high precision isn't always called for if we're calculating something from measurements whose precision is limited. And significant digits, following the rules for significant digits as we do calculations with measured data, will ensure that we don't express final results with a greater precision than is called for by our measurements. You know, a good example of this, just to wax poetic about this for a second, is taking the square root of a number. Say we make a measurement and that measurement is 5 grams, and for whatever reason we need to take the square root of that measurement. The square root of 5 is, I believe, an irrational number, so it's going to be a very, very long string of digits. But most of those digits are entirely uncertain given that our original measurement was only 5 grams, right? 5.0, maybe something, 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 we don't know. So with only one digit of precision in our measurement, we shouldn't get a ton of digits in the square root of that measurement. We should really only get 1. This is the spirit of significant digits and why there are rules when we multiply, divide, add, subtract measurements. Now, what is a significant digit? Significant digits are non-placeholding digits that communicate the value of a measurement rather than its power of 10. So, as we'll see on the next slide, any digit that is not 0 is automatically significant, and where these get complicated is how we deal with zeros. We'll come to that in a second. An equivalent way to talk about significant digits is significant digits are the digits in a measured value that appear in the significand when we write the number in scientific notation. So say, for example, we make a measurement, 105.55 grams is what the balance tells us. We write that down, and then we want to express this in scientific notation. We would do the usual dance of move that decimal point over just to the right of the leftmost number. We had to go 1, 2 spots to do that, right? And so the significand is 1.0555. We're going to include all those digits that the measurement gave us times 10 to the 2 grams. And the 10 to the 2 is not part of the significance of this number. The 10 squared is purely there to set the place, right? To basically tell the reader, the viewer, that 105.55 is the magnitude, the power of 10 corresponding to the measurement. So all the significance is built into this significand 1.0555. And as you may have guessed by now, this is why we call this number the significand, because it holds all the significant digits in the measured value. If we've got a value before us and we're interested in determining the number of significant digits, we can do that by following the rules that you see on this slide. Rule number 1 is pretty obvious. Any number that is not 0 does communicate something about the value of the measurement, and these are always significant. These are always significant digits. You never want to discard these. You never want to throw one of these away if it appears directly in a measurement. For example, if you're taking a mass on a balance, write down the 5.5 and use the 0.55 as much as you can, right? Since we're going to trust the balance, that the balance is precise to this level, since the LCD display is showing us that number, right? So non-zero digits are always significant. A 0 that shows up between two significant digits is also significant. So say you've got a number, something, 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 203, something, something, something. The 0 between the 2 and 3 is significant because, again, it communicates something about the value. If this was not there, this would be 23 instead of 203, for example. So that 0 is a significant digit. Leading zeros, numbers that appear at the beginning of a number, are never significant. And the classic example of this is the 0 that comes right before the decimal point in most reported values. If you're I was always in grade school a 0 point blah, blah, blah person when I was writing decimals, right? Always wrote that leading 0. That leading 0 is never significant. If you have leading zeros for a number that is less than 1, quite a bit less than 1, things like 0.000382, those leading zeros before the 382 are not significant. Zeros at the end of a number, on the other hand, and after the decimal point are always significant. The reason is the entire motivation for writing down the 0 is to indicate significance. If we make a measurement, say, on a balance, and the balance says on its display 5.80 grams, we want to write down that 0. If the balance only says 5.8 grams, say it only measures to the nearest 0.1, we are not going to write down that 0. So if you see that 0 on the end of a value to the right of the decimal point, it's always significant. Now, to the left of the decimal point, this gets a little ambiguous, and this is the idea of rule number 5. Zeros at the end of a number and before the decimal point are not significant. These are just placeholding zeros, kind of like the leading zeros in a number that's less than 1, unless a decimal point is present. So here's an example where the trailing zeros after 732 are not significant because the only purpose of these zeros is to act like a kind of metric prefix, right? These 3 zeros are the same as like a kilo prefix, right? 732 kilo whatevers would be equivalent to this value. So those are just placeholding zeros. However, if we place a decimal point after that last 0, this is a visual indication that we wrote these zeros down to indicate that the measurement was made in such a way that the display of our measuring device had 000 on the display, indicating that these digits are part of the precision of the measurement, that the measurement is precise to the ones place. Without the decimal point, this measurement is only precise to the thousands place in this case. And the last thing to note as you're looking at numbers and evaluating significant digits and doing calculations is if you ever bring in a purely mathematical quantity or a counting number, 1 atom, 2 atoms, 3 atoms, etc., These don't limit the precision of calculated results at all and have no effect on significance. You can think of them as infinitely significant in a way. Things like pi, e, mathematical constants don't affect this, nor do counting numbers. You can ignore them completely when you're thinking about significant digits in calculations. Where the rubber really hits the road with significant digits is when we start doing operations with measurements, arithmetic, addition, subtraction, multiplication, division, raising the powers, exponentials, logarithms, all that fun stuff. And so now we're going to survey how we think about significant digits in the context of arithmetic operations. So the idea for addition and subtraction is that the final result of the addition or subtraction has the same level of precision as the least precise measurement. And the level of precision is indicated by the place of the last significant digit on the right. So for example, in this subtraction of two volumes, we have a volume that was measured to 0.1 milliliter, and we have a volume that was measured to 0.0001 milliliter, presumably by a vastly different method. This is actually not very common in practice to have measured quantities that we're adding or subtracting with vastly different precisions, since we're usually using the same method or the same instrument to make both measurements, but just for the purposes of illustration, this is good to see. We can do the subtraction. We get this obnoxious number when we punch that into our calculator, but because the least precise measurement involved was only measured to the closest 0.1 milliliter, our reported result needs to be limited to the closest 0.1 milliliter. A second example on the right shows this idea as well. 83.5, that's to the nearest 0.1 milliliter. We're adding to that a volume that's to the nearest 0.01 milliliter, but our final reported result, even though our calculator is saying this, our final reported result is going to be rounded to the nearest 0.1. We'll actually talk about rounding here in a second and how this works in the more ambiguous cases. So the idea with addition and subtraction is look for that sort of least precise measurement, the measurement that ends at the biggest place value, and make sure that that biggest place value is the last digit reported, the furthest to the right digit reported in your final result. For multiplication and division, this is, at least to me, a little bit simpler to kind of track down. The idea here is that the final reported result has the same number of significant digits as the least precise measurement. It's the measurement with the smallest number of significant digits. It's a very conservative convention, right? If we're taking a bunch of numbers, multiplying them together, say we've got 3 lengths, and 2 of those lengths have 2 significant digits, and 1 of them has 4, when we punch this into a calculator, we'll get a ton of digits, but we're going to round this value so that the final result only has 2 significant digits, since that number of digits, significant digits, matches the number of significant digits in the least precise measurement, which is here 9.2 or 6.8. Either of those would lead us to the conclusion that the final reported result should have only 2 significant digits. So again, just to sum up, addition and subtraction is all about place value. Find that biggest place value where the numbers you're adding or subtracting get cut off. And then for multiplication and division, it's actually much more common to run into issues of different levels of significance for measurements, since we'll often be multiplying or dividing different types of quantities, different types of measurements. Use that measurement with the least precision, the fewest significant digits, as your barometer for how many digits should show up in the final reported result. Now, let's talk about rounding a little bit. And actually, the first thing I'll say about this, and we'll return to this at the end of the slide, is your mileage may vary with this. Different instructors will tell you different things. This is, in my mind, sort of the prevailing convention, and it's the one that I generally use. Rules 1 and 2 are pretty straightforward. If we need to round a number with the first digit removed greater than 5, we're going to round up. We're going to take that least significant digit, that's the smallest digit further to the right that we're going to retain in our final reported result, and increase it by 1. So 5.379 becomes 5.38. 5.38 becomes 5.4. We round up when that first digit removed is greater than 5. highly intuitive. The other side of the coin is also straightforward. If the first digit we're removing is less than 5, we're going to round down. So 0.2413 rounds down to 0.241. 0.241 rounds down to 0.24. Highly straightforward. It's the second half of these rules where things get weird when the first digit we're removing is equal to 5. It's unclear whether we should round up or down since 5 is in the middle between 0, 1, 2, 3, and 4 and 6, 7, 8, 9, right? Well, I guess in the case of a 0, you wouldn't round at all, right? So 1, 2, 3, 4, 6, 7, 8, 9, 5 is right in the middle. What do we do? A rule you'll often see is if the preceding digit to the 5 is odd, round up, and if the preceding digit is even, round down. So here, for example, 0.415, if we need to round this to the nearest 0.01, the 1 in 15 is odd, and so we're going to round up since the 5 is the only digit we're removing. We'll get to more than just the 5 in Rule 4. But on the other hand, if we're rounding 0.445 to the nearest 0.01, because the 4 in 45 is even, we're going to round that down to 0.44. So this is a rounding convention that avoids biasing when you round. What it does is, theoretically anyway, you get equal numbers of rounding up and down so that rounding doesn't bias your data to be a little bit too large or a little bit too small, depending on your rounding convention. Now, when you're removing more digits than just 1, and the first digit is 5, we've got rule number 4. You're going to round up in that case, applying rule 1 essentially. The chunk that you're rounding is bigger than half of the range of numbers that you're looking at for the bit you're removing. And so we're going to think of that as bigger than half the range. Rounding up is the idea. That's just rule number 1. If all subsequent digits are 0, then the measurement is sort of equivalent to a rule 3 measurement. So then you're going to apply rule 3. So for example, say we had 8.6252 and we wanted to round this to the nearest 0.01. Well, the 52 that we're removing is bigger than 50, right? And so this is bigger than halfway between 1 and 99, and so we're going to round that up to 0.863. On the other hand, if we had just 8.62500, now we're back to rule number 3, where this is an even number, and so with all the digits after the 5 equals 0, this is equivalent in rounding anyway to 8.625, so we're going to round that down to 8.62. And all of these rounding rules, I wouldn't even sweat until the very end of a calculation. But just like the rules for rounding in general, this is a thing where your mileage may vary, YMMV. This tends to be my policy, where I'm not an analytical chemist. I'm not a quantitative chemist in my background, and so I'll often avoid rounding or even really thinking about significant digits until the very end of a calculation when I'm ready to report a result. And I should say it is very important to think about significant digits at that point, because again, it's a matter of scientific integrity and reporting results with appropriate levels of precision, since including too many digits in a reported result gives the reader, gives the public, gives the government, gives your audience a false sense of precision, a false sense of confidence in your results.